Okay, good morning, students. Welcome back to our webinar session. We're discussing Chapter 9, Electromagnetic Induction, and in the other class we stopped at eddy currents concept. Okay, so eddy currents, just it is nothing but induced current which is generated due to the change in magnetic flux in metallic blocks, not in the case of coils. Okay, we discussed all the concepts using coil, but here the eddy current is related to the metallic blocks in irregular shape. Okay, it's not, there is no specific shape. It's not like any coil. So any metallic plates. So as we have seen in the diagrams here. So the copper plate is allowed to swing like a simple pendulum, right? So between the poles of the strong magnetic field. So already we discussed this thing that whenever the plate is kept in between the strong magnetic field and it is allowed to oscillate in between the strong magnetic field, then the number of lines of force which are passing through means linked with that metallic plate is continuously changing, because metallic plate is also moving, so area of cross section is also changing. Then the number of, there is flux, magnetic flux, or number of lines of force which are entering into that metallic plate also changes. So it's nothing but changing magnetic flux. And we know what happens if there is a change in magnetic flux, that then if it is a coil induced EMF will be generated, and here it is not a coil, it is a metallic plate. In this induced current will be generated, because here the charges are itself aligned to move in a particular direction. So as the shape is in spiral kind of thing, and that's why the name is eddy current or Foucault currents that we discussed in the last class. That here, so it is found that the motion of the plate becomes a damped. Motion of the plate becomes damped. Damping means coming to rest. Okay, from the maximum oscillations to the slowly as time increases comes to rest. So that is the damped oscillations. So it is found that the motion of the plate becomes damped and comes to rest in the field due to electromagnetic induction. So why it is coming to rest means, here whatever the induced current is generated in the metallic plate, that always opposes the cause produced it. This is Lenz's law. Okay, so here the whatever the induced current is generated, that current opposes the cause. Who is the cause here? Who is the cause? Magnetic flux, change in magnetic flux. So here between the south pole and north pole, just opposes the strong magnetic field. So whatever the induced current is generated in the plate, that opposes the magnetic field. Slowly, if you see this diagram here, while it is entering into, means in between the two poles, here this whatever the induced current is generated, that opposes, it is not allowed to enter into that. Similarly, once it is means due to the gravitational field, means force, it is enters into that, and the moment it enters and crosses that, have seen it crosses with a certain velocity. So during crossing also, again what happens, the direction of induced current changes. So due to direction of induced current is changed, then what happens, it opposes opposes the motion. What is that opposition? Moving away. Moving away is the action, and what is the opposition? Oppose that action. It is not allowed to move away. And first case is what? It is reaching between the two poles. The metallic plate is reaching between the two poles, that is not allowed. That means it is not allowed to come. And here, after leaving this poles, again the same thing is happening, that the induced current is not allowed to go out. So in both the cases, it is opposing the action, opposing the cause. Okay, so with a better example, we will see one more here. As the plate moves in or out, as the plate moves in and out of the field. Okay, as the plate moves in and out of the field, then the magnetic flux associated with the plate is continuously changes. I told you, whenever this metallic plate is under motion, is cutting the lines of force between the two poles. Okay, lines of force between the two poles. It is always under motion, then always the number of lines of force which are passing through this metallic plate changes. So due to this change, what happens? Induced eddy current will be generated. Induced eddy current will be generated. So that keep in mind. So this is the point. It's the main concept. Now eddy current opposes such that the plate swings into or out of the field region between the poles. So what eddy current function here? Eddy current opposes the cause. Opposes the cause. What is the cause? Change in flux. Okay. So eddy currents are opposed such that while the plate enters into or out of the field region between the poles. That's what we discussed. Okay. But whatever the induced current is generated, see, observe this diagram. Arrow, this red arrow indicates that it is moving inside with a certain velocity, moving inside with a certain velocity. So while it is entering into the field, the current is generated, current is moving in anti-clockwise direction. Current is flowing in anti-clockwise direction. Then the force is outward. The force is outward. Means what is doing here? It is pushing out. It is pushing out. The force is outward. While the plate is moving inward with a certain velocity, then induced current will be generated. What this current will do? Opposes the cause. That is, it is not allowing. What is the cause here? Change in magnetic flux. Why it is changing? Why it is changing the magnetic flux? Because it is entering into the field. So that is the reason. So what this induced EMF will do? It opposes. So not allowed to come into the magnetic field. So this is force acting on this body. Similarly, once it is entered with a certain velocity and leaving, observe this diagram, leaving this magnetic field, this metallic plate is leaving the magnetic field. So while leaving also what happens? The flux changes continuously. So due to this change, what happens? Induced EMF will be generated. Look at this, it is in a clockwise direction. Then what happens? The block is leaving the field, but it is attracting, opposite to that. It is attracted to a pulse inside the field. Pulse inside the field. Understood? So eddy currents are opposite such that the plate swings into or out of the field region between the poles. Okay, so eddy current is formed due to change in magnetic flux linked with the metal. Eddy currents are formed due to change in magnetic flux linked with the metal. Right. So here, eddy current opposes the motion which causes the change in magnetic flux. So always, whatever the eddy current is generated, so what's its function? It always opposes the cause produced. What is the cause? Change in magnetic flux. That is what? That is due to while it is under oscillation. So it stops the oscillations in very short interval of time. Originally, that is swings, I told you per minute, for example, it is taking 10 oscillations, but due to this magnetic field and due to this eddy current, what happens? The number of oscillations decreases because this external force is acting. Sorry, the force is acting. That is opposition by the induced current is acting on these points. Okay, eddy currents oppose the motion which causes the change in magnetic flux. Right. So whenever the eddy current is flowing in the metal block, heat will be generated due to resistance of the metal. Remember, this is one of our applications in eddy currents, that whenever the eddy current is flowing in the metal block. Whenever the eddy current is flowing in the metal block, heat will be generated due to the resistance of the metal. So here, this is a metal, for example. So metal, in this I told you, all the 3 electrons will move in random directions. But when it is kept in the external magnetic field, they are aligned to move in a particular direction. Then what happens? As the current is induced in this, then heat also produces because of the resistance of the metal. See, all the metals having some, possessed with some resistance. So due to that resistance, heat will be generated. So to minimize the heat, so many methods are there to, first of all, to decrease the surface area of the material and all. Okay, so here if you reduce the, if you minimize the surface area of the metal, then what happens? The induced EMF generation, amount of induced EMF is also decreases, so that heat also, heat dissipation is also minimum. Okay, so that we are going to see the applications of eddy currents in our daily life. Right, so here one of the important applications, that electromagnetic damping. I told you that the damping is what? Coming to rest within very short interval of time. Yes, electromagnetic damping. So usually we see the electronic instruments like galvanometer, ammeter, voltmeter. Those are what indicates the readings over there. Okay, actually that needle is connected with some coil. I have observed this diagram. Coil is there. So on this coil, the magnet, a small magnet is kept over here. Okay, then when it is connected to external power supply, then its coil gets induced current. Then due to that change in magnetic flux and all, so here direction of current which is flowing through this coil also changes. Then due to that, the induced EMF will be generated, and this magnet is also started to oscillate over there. Okay, then according to the needle also oscillates. So, but it should come to rest immediately. Okay, how much current is, for example, it is a galvanometer. Okay, if it is connected to the current, then whenever the current which is flowing through the circuit, then what happens? It shows some reflection. So that reflection should exactly stop. Means this needle should stop at a particular point. Otherwise, what happens? It continuously oscillates. Okay, so means to stop that needle, it will require more time. Okay, it takes more time. To avoid that, what we are doing is, see here, that is electromagnetic damping that we are using this eddy currents concept. So what the eddy currents portion is, of course, the cause. So just now we discussed that within very short interval of time, it comes to rest. These are called damping oscillations. So damping measuring, okay, right? Damping in measuring instruments like galvanometer, okay, damping in measuring instruments like the galvanometer. Then when the coil oscillates, then the eddy current is generated and then opposes the motion of the coil and bring the needle to rest quickly. This is what we require. Okay, so that's why in electronic devices, okay, especially for measuring instruments like, then the needle should come to rest quickly, so that we use this concept, that is eddy current concept. Here we use what? Coil comes to rest only when the eddy current is generated and opposes the motion. So within very short interval of time, it comes to rest. So this is one of the important applications of eddy currents. Yeah, and here is one more application, that is magnetic braking. You might have heard about this, is electronic trains, that means a braking system, magnetic braking system, that you might have heard about this. This is due to what is eddy currents concept. Okay, so here magnetic braking, the strong electromagnets are fitted just above the railings in electrically powered trains. So due to this eddy currents induce in it and oppose the motion of the train. So you can see this construction now. So this is the part of the train, that the upper part of, means to the train, this magnetic system is connected. Okay, so look at this motion direction here. Okay, so here you can see north south magnetic, strong magnetic fields are kept out there, and is raining here. Okay, there is a raining. Okay, so then what happens here? Look at this, eddy currents are generating here. Look at this, eddy currents are generating. Okay, due to change in magnetic field, what happens? Eddy currents are generating on the tracks, that is rails. Then what happens? Due to the eddy currents, what happens? It is opposes the motion. Okay, so due to motion means due to motion, train is under motion. So due to motion, what happens? There will be change in magnetic flux. So then nearby, what is that? One metallic plate, that is rail is there. So that's what that opposes the motion of this body. That is what cause producing. Who is producing cause? Who is changing magnetic flux? Motion train. So then it applies that it is opposes the motion, right? It just like acts as a magnetic brake. Okay, so here also you can see this. So this is what is a magnetic material, magnetic plate here. Sorry, metallic plate here. So metallic plate here. Okay, so while it is changing, what happens? While it is moving, what happens? The surface area changes. So surface area changes, then what happens? Then the magnetic flux changes. So whenever there is a change in magnetic flux, then the metallic block, the eddy current will be generated. So what is the eddy current? The function is oppose the cause. So what is the opposed cause? What is the cause here? Motion of this metallic block. So motion of the metallic block is the cause for the change in magnetic flux. Then whatever the induced current is generated in the block, that opposes the motion. So that is used as a magnetic brake. Okay, so here you can see the picture of this mechanism under the train here in this diagram. So here magnetic braking is that strong electromagnets are fitted just above the railing and in electrical power trains, and due to this eddy current induced in it. Okay, due to this eddy current is induced in it and opposes the motion of the train. So this is also one of the important applications. Yeah, and one more application is induction furnace. Induction furnace, this eddy current generates high temperature. I told you, due to the resistance, heat will be generated. So that heat also we are using. Okay, in a proper manner, that is induction furnace, and see how much current, how much heat is liberated. So that depends if the material having more resistance. Okay, the material having more resistance, then more heat will be generated. More rupture means more collisions takes place inside the material. Remember, okay, inside the material, due to induced current, in the metal, okay, all the charge carriers are moving rapidly. Then what happens? Due to the number of collisions inside that, the lots of heat will be generated. So here, eddy current generates high temperatures due to resistance in the metal, and so it can be used to melt even the heavy metal blocks. Okay, so especially for the industries. Okay, so industries, they use this concept, that is eddy current concept in induction furnace concept. Okay, right? So induction furnace means what? To boil, to produce heat, to produce temperature. At what temperature even you can melt the metal blocks. Okay, especially in steel plants. Okay, so there they will melt the garbage, means waste of metal blocks. Wastage of metal blocks, they will convert into molten metal. Okay, so there it requires more temperature. So here is the principle we are using, eddy currents. Okay, right. So now we'll move on to the next point. Is next concept is one more application is there. So this phenomena can be used in the induction motors like fans, coolers, etc. Okay, especially low power and low rotations per minute motors. Means RPM, whose RPM is very small. See, this eddy current concepts can be used in the induction motors like fan, the ceiling fan. Ceiling fan is an example of that only. Whenever the magnetic means there will be a coil. You can see if you open that, there will be a coil, a copper coil will be there, copper winding will be there. So that produces the induced current. Then shocks will be there. So in one part the coil is acting, the another one also starts rotating. Okay, so here is what this, especially this will be used in only the motors such that whose RPM is very small. They cannot be used in heavy motors like pumps and all. They can't use over there. Okay, they can't use because it requires more consumption. Okay, it requires more energy. See, that's why especially these will be used in. See. Have you observed fans and coolers and especially this low RPM motors? They produce very small CA diodes and all. So those will give very low sound, low noise. Okay, for them RPM is very small. So for them we use the eddy current concept. Whereas in high power motors, they will produce more noise. Okay, so for that more energy is required. So this concept is not useful over there. Okay, so and also analog electric power meters. Yes, see in this power meters nowadays these analog systems are not there. Only digital power meters are coming. But in olden days, that you can see an white metallic disc kind of arrangement that is continuously rotates. So this is also, see, this is because of the eddy currents. Okay, so it is rotating, the change in magnetic field. Due to the change in magnetic field, what happens that induced current will be generated. Okay, so this is calls for what? It's continuously rotating and gives a reading for this. Okay, so everything, whatever we discussed, the whole concept is involved in this. This is works under which principle? It is eddy currents concept. So this is also one of the examples for eddy currents concept that in this word is power meters is very important. Power meters, analog power meters, in this eddy currents are used. Okay, so these are the applications important. Okay, as per IPE, so these 4 or 5 that as per your availability that you can go through. Okay, so now we'll move on to the very important concept is a self-inductance concept. Okay, self-inductance. So up to now you understood what is induction. Okay, how the induced current will be generated, that you understood now. Okay, so as per the Faraday's law, as per the Lenz's law, so what is the phenomenon for getting the induced EMF, okay, induced EMF, and what is Lenz's law says that whenever this induced EMF is generated, that opposes the cause, that is what is the Lenz's law. So based on this, we are further moving to the another concept that self-inductance. See here, for the self-inductance, see, that's our own concept on this, that what we discussed in Faraday's laws and Lenz's law. See here, look at this. There is a coil, see blue colored line, okay, is a coil in this diagram. So the moment the battery is connected, okay, the positive and negative. So the current is moving, okay, the current is moving in this direction through this coil. Okay, so as per Oersted experiment, whenever the current is flowing, then what happens? The magnetic field will be generated. So you can see the magnetic lines over here. So through the solenoid, so it's a solenoid now. So through this solenoid, the current is flowing, and definitely what magnetic field is also generated due to the induction. Okay, so now observe. Whenever this current is flowing, the magnetic field is generated. Now, for example, there is a change in current. There is a change in current. Okay, for example, there is a change in current. Then what happens? The magnetic field which is generated due to this solenoid also changes. I am repeating. Just for constant power supply, the constant current will be generated and constant magnetic field also will be generated. But for example, the current which is flowing in the circuit is varying, changing continuously. then the amount of magnetic field which is generated in the coil also changes. Then what happens? What happens? We know that whenever there is a change in magnetic flux, then what happens? Inside the coil itself, induced current will be generated, induced EMF will be generated. Okay, so both the phenomena are happening in the single coil. In the very beginning of this chapter, we considered two coils. Okay, three experiments we have done. We considered three coils. So, sorry, two coils. So, in those two coils, in one coil we are producing a magnetic field, and due to change of magnetic field, the other coil is getting induced current. Okay, but here observe the whole concept is happening in a single coil. That's why the name is a self-inductance. It's a single coil. Understood? So now we move on to this. It is a phenomenon of flux made by the coil linked to the coil itself. That's why the name self-inductance. What is that? Whenever the coil is connected to the varying current. Okay, varying current. Then what happens? Varying current. Then what happens? Magnetic flux also changes in the coil. Magnetic flux also changes in the coil. So this change in magnetic flux produces induced EMF in the coil. Now look at this the small circles over here. So small circles are nothing but another change in magnetic flux. This is magnetic flux, and observe this induced EMF is generated. Okay, induced EMF is generated, and again that induced EMF opposes the original cause. What is the cause? This current. What is the cause? This external EMF. External, you connected through battery. So opposes this battery now. Understood? Opposes the external EMF. Okay, so what is the name here? Self-inductance means in a single coil, the whole phenomenon is happening over there. That is, the coil itself acts as itself is linked with the magnetic field, and itself behaves induced current will be generated, and itself is opposing the cause producing it. Opposes the cause producing. Who is the cause here? Changing external EMF. Changing external EMF. So it is the phenomenon of flux made by the coil linked to the coil itself. Okay, so that is what. Now, due to this linking, an induced EMF is generated. Okay, got my point. So the whole discussion is kept over there. See, due to this linking, an induced EMF is generated. Okay, so due to change in magnetic flux, because the current is changing, then magnetic flux is also changing. Due to that change in magnetic flux, induced EMF is generated inside the coil itself, in the same coil. But we used in the previous discussion, we used another coil in its vicinity. Okay, in its area, we used another coil so that that coil gets affected. Means in that coil, induced EMF is generated, but we didn't use another coil here. But in itself is creating induced current, and that current is of course the original external flux. So here, see. It's a concept to understood here. So the current I is increased, then flux linked with the coil also increases. Okay, changes means what? If the current is changed, the flux is also changed. Magnetic field also changes. Okay, so magnetic field is nothing but lines of force. So these lines of force passing through that solenoid, it also changes. It's nothing but magnetic flux is changing. So magnetic flux is directly proportional to applied current. So flux purely depends on what? The amount of current you supply. Amount of current you supply to the coil, then accordingly that much magnetic field or magnetic flux will be generated. So magnetic change in magnetic flux depends on what amount of current that you supply. So here is the equation that phi is proportional to I. Phi is what is the magnetic flux, is directly proportional to I is what amount of current which is flowing through the circuit. So phi is equal to, so to avoid this proportional, we are using one constant, that is phi is equal to Li. Okay, look at this expression, equation 1. So remember that we are going to use this in the derivation, coming derivation. So where L is called coefficient of self-inductance. Okay, so where L is called, is a constant, is a coefficient of self-inductance, coefficient of inductance. Okay, so here the whole either flux or current depends on this inductance constant. So look at this change here. So here from this take out the L value, means if you want the expression for self-inductance, so I told you L is what coefficient of self-inductance. If you want the expression for the self-inductance, so take out L here, then it will be pi by I. Okay, L is equal to pi by I. So here, what is the ratio here? What is the relation between them? If I increases, if the current which is flowing through the circuit increases, then the magnetic flux which is generated in the coil is also increases. So both are directly proportional. Now what happens? Here we got the expression for what? Self-inductance. Then how much how much is the value of this self-inductance? If you want to know, then make in this circuit to allow only 1 ampere of current. I'm repeating, 1 ampere of current which is flowing through the circuit. Look at this expression, L is equal to pi by I. Then if I becomes 1 ampere of current, means for 1 ampere of current, then what will be the self-inductance? What will be the self-inductance? So the self-inductance is equal to, observe this equation. So yeah, L is equal to pi. L is equal to pi. So if the current of 1 unit is flowing in the coil, then the coefficient of self-inductance L of the coil is numerically equal to flux linked with itself. Okay, so what is the value for this one self-inductance? What is the value for the self-inductance is? It is numerically equal to, means for example, due to 1 ampere of current, for example, 20 Henry, okay, magnetic flux is generated. Okay, then what will be the L value? So L is equal to 20. L is equal to, numerically equal to what? L is equal to the value of magnetic flux. That depends on what? The amount of current to be supplied. So if that current is 1 ampere, then whatever the value, whatever the magnetic field generated, that equal to the self-inductance. So, okay, so the coil is numerically, inductance is numerically equal to the flux linked with the coil. Now, units for this, if you see the unit, so here it is what the expression L is equal to pi by I. So pi is what? Weber, okay, and I is measured in ampere. So Weber by ampere is equal to Henry. Okay. So what is the unit for self-inductance is a Henry. Okay. So continue this as to calculate the EMF for due to self-inductance. What is self-inductance? In the single coil, the whole phenomena is going on. Okay. So single coil itself producing the induced current. Now, what is the expression for the induced EMF? Okay, so what will be the expression for the induced EMF? That we know the flux generated in the coil is. So take that coil as an example. We know that phi is the magnetic flux generated. Okay, we know the expression phi is equal to B dot E, that is vector form, that is B dot K, that is magnetic field, applied magnetic field is product multiplied with the area of that cross section. So pi is equal to, means what will be the B value here? Magnetic field due to the solenoid, that you know that we know that mu naught n I a. Okay, B value is mu naught n I a into a. Okay, B value, that is magnetic field associated with the solenoid, is mu naught n I a. Mu naught is the permeability in free space, and n is the number of turns associated with the coil, and I is the amount of current which is flowing through the coil. So in this expression, if you observe, mu naught is constant, number of turns will be fixed, and area of that cross section will be fixed. Then what is changing here? I is changing. That you can change I value. So if I is changing, what happens? The pi also changes. Okay, if the current is increases or decreases, then the relevant magnetic field is also changing. Okay, so here, so yeah, this equation will become what? Pi is proportional to I. Then already we move from the Faraday's second law. E is equal to minus d pi by dt. Now what you observe here, if I is changing, magnetic flux is also changing with respect to time. Okay, so the amount of magnetic flux changed with respect to time. Okay, pi is changing with respect to time. That is equal to EMF. That is equal to electromotive force which is generated. Okay, which is generated in the coil. Okay, this is Faraday's second law that we discussed. Okay, second law is what? Second law states that amount of induced EMF. Okay, amount of induced EMF is generated due to change in flux. So this flux is changing with respect to time. That is, rate of change of flux is equal to amount of induced EMF is generated. So here negative means what? It is always opposes the cause producing it. Okay, then already we discussed that we know that pi is equal to Li. Okay, that pi is equal to Li. Okay, so L is what? Self-inductance. Now substitute this pi value in this expression. E is equal to minus d pi by dt. E is equal to minus d pi by dt. So substitute in the place of pi is Li, then E is equal to minus d by dt into Li. Because L is constant. L is what? Is a coefficient of self-inductance. It's a constant. So take out L value. Then what happens? What is remained? Di by dt. So current is changing. Okay. So current is changing with respect to time. Then magnetic flux will be changing. So that change in magnetic flux produces what? EMF. Induced EMF will be produced. So that's what. So an induced EMF is developed in the coil E is minus L di by dt. Minus L di by dt. Where di by dt means what? Changing current. Okay, changing current, rate of change of current. So now if this rate of change of current is 1 ampere, for example, okay, we are obtaining the expression for what? Induced EMF in the self-inductance process. Means in the same coil, how much EMF will be generated if 1 ampere current is applied. Okay, so if the rate of change of current is equal to 1 ampere per second, then see, observe this dl by dt, sorry, di by dt is equal to 1, then what else is remained? Then E is equal to minus L. So what you observe here, the EMF is equal to, what is this? L means what? Coefficient of inductance, coefficient of self-inductance. So finally, so whatever the EMF is induced in the coil is numerically equal to the coefficient of self-inductance. So that depends on what? Amount of current which is supplied, so that the induced EMF is also changes. So whatever the EMF is induced in the coil, that is because that is equal to the numerically equal to the coefficient of self-inductance. See here, negative sign indicates always it is opposite. Okay, induced EMF is always opposite the cause. Okay, so this is about the expression for the EMF produced in the self-inductance. Okay, so what is that? What is self-inductance? It is the device. Okay, so that itself changes the magnetic field. That itself produces, means in the same coil produces an induced EMF. Same coil produces EMF and that opposes the external EMF. Okay, and we have done the expression and theory. Now we move on to the next is the mutual inductance. Mutual inductance. Here, mutual inductance is also the simple concept that it is a phenomena in which the flux is linked to one coil changes accordingly with the change of current in another coil's vicinity. Okay, it is the phenomena in which the coil, okay, in which the flux is linked to one coil changes accordingly with the change of current in the another coil's vicinity. So here we are considering two coils here, but in the self-inductance we consider only one coil. Means the single coil itself behaves, exhibits two properties. But here we are taking two coils here. Okay, two coils we are considering here. That look at this. Coil one is connected a power supply, that is AC source. AC source we connected. Then look at this, the current is flowing in this direction through the coil. The current is flowing in this direction through the coil. Okay. Then what happens that we know inside the coil, what magnetic field will be generated. Right. Now nearby one more coil is kept over there. Just it is connected to a galvanometer. So we use two coils here, coil 1 and coil 2. So it is the phenomena in which the flux is linked to one coil that changes accordingly with the change of current in another coil vicinity. So here in this, for example, in this, see, why you see the AC here, it is alternating to changing. Okay, continuously changes with respect to time. That is alternating. Okay, continuously with respect to time, it is changing. So that's why we are using the AC generator here. Okay, so here, as we use the AC generator, the current is also fluctuating. So whenever the current is fluctuated, the magnetic field which is generated is also not constant. That is also fluctuating. So it's nothing but what the magnetic flux is changing. So due to change in magnetic flux, what happens? Then induced current will be, induced EMF will be generated in the neighboring metal conductors. Okay, so here next coil 2 we use here. So in this EMF will be generated. If that EMF is connected to any external circuit, then the current will be flow. Okay, so here we use the galvanometer here. So look at this, the whole setup here. We use the two coils. Then with respect to each other mutually. Okay, one is changing the current, another one is producing the EMF individually. Okay, so that's what this one coil is changing the current accordingly. Then the another coil is getting induced EMF. Okay, flux is linked to the one coil, changes accordingly with the change of current in another coil. So nearby another coil is kept over there, then that is also producing induced EMF. So here observe these points. Magnetic field is produced. Magnetic field is produced in the coil. Okay, that it's a value, that is amount of magnetic field is produced here. Mu naught and I here. Okay, so that you know, see, this is the magnetic field generated due to this coil. Okay, sorry, and due to change in current. Current is changing continuously because the AC generator, AC source we are using, and due to change in current, magnetic field also changes. Okay, magnetic field also changes. That is generated in the coil. And due to this change in magnetic flux, then what it produces, what it will be producing? So change in flux is also produced due to this change. With change, magnetic field is changing, then magnetic flux is also changes. So how much it will be? Pi is equal to NBA. Okay, pi is equal to NBA. Pi is equal to that, you know, B into A. No? So here that depends on the number of coils connected to this, number of coils. Okay, N. So amount of flux depends on that surface area and all, okay, cross-sectional area. So the magnetic field is changing now due to change in magnetic flux. Due to change in magnetic flux, induced EMF is generated. So this is an expression that we know. Okay, so that is Faraday's second law, that E is equal to minus d/dt. Okay, so pi is equal to that, pi is equal to NBA, and due to this change in the NBA, induced EMF is generated, that is minus d/dt. Okay, so just to get this discussion. Okay, so how it is changing here, right? Coil 1 is creating changing flux, and coil 2 is induced EMF, creates an induced EMF. So these are expressionally, mathematically we are representing this, right? And here, let the current in the coil 1, the current in the coil 1 is I1, I suffix 1. See, this numbering is of course important, but it is only for identification. Okay, let the current in the coil is I1. Means, in that current in the coil 1, okay, so amount of current is moving I1. I1 represents the current in the coil 1. I1 suffix I represents what? So 1 represents what? Coil 1. Okay, let the current in the coil 1 is I1. Now flux linked with the coil 2 is, flux linked with the coil 2 is pi suffix 2 1. This notation is magnetic flux in the coil 2. Suffix 2 1 means what? Magnetic flux in the coil 2 is due to coil 1. Okay, 2 1 means what? Magnetic flux is generated, okay, in the coil 2 due to coil 1. And this magnetic flux is proportional to current I. Okay, that we know. In the coil 1, if there is a change in current, okay, in coil 1, if there is a change in current, then the amount of lines of force or magnetic flux linked with the coil 2 is this much. Okay, pi 2. That is also changes. If the current changes, amount of lines of force which are flowing through the circuit or in second coil is also changes. So to avoid this proportionality, we are using constant here. Okay, to avoid this proportionality, we are using this constant, that is pi 2 1 is equal to MI1. MI1. Okay, so here M is what? M is a proportional to constant, is called, M is called coefficient of mutual inductance. Comparison, self-inductance, we use the notation capital L, and here capital M is the mutual inductance. And let us see the value for this also, where M is constant of these two coils called coefficient of mutual inductance. Okay, so for these two coils, we are using one constant. This constant is valid for together, means both the coils. This constant is valid for both the coils, right? So that's why it is a mutual inductance. Right, so automatically, if you see, if you want to get an expression for the mutual inductance, then take out the M is equal to pi by I. Just I avoided, just I remove this notation. Okay, just I remove this notation. So M is equal to pi by I. Then in this couple of coils, if the current in the coil 1 is 1 ampere, then automatically we will get an expression M is equal to pi. If I is equal to 1 ampere, then mutual inductance is equal to pi value. Okay, so with this we will conclude with this session, and in the next concept we will continue the next class.